Hello everyone, good morning. First, I would like to convey my sincere thanks to the organizers and the judges of 2022 Symposium on Nano-Device Circuits and Technology for recognizing my research work with a special prize. Today, I am glad to share my recent research findings to the distinguished scholars and my fellow researchers gathered here. The title of my talk is the first principle theory and experimental evaluation of low-dimensional beta-gallium oxide in resistive switching memory. Let me start the presentation with the outline. I will start with the motivation to study resistive memory and low-dimensional gallium oxide first, and then we'll discuss the results from experimental observations of RS memory and first principle calculations on the effect of oxygen vacancies. Resistive memory is one of the promising candidates in the emerging non-volatile memory technology and exhibits many advantages over its counterparts as shown here. Unipolar and bipolar switching are the two types of resistive memory based on IV curves. Further, resistive memory is classified into several groups based on the switching mechanism, one of which is called valence change memory, where the on and off process of switching results from the formation of oxygen vacancy conductive filaments between sandwiched metal electrodes. It is the most reliable and consistent RS memory type generally observed in the metal oxide materials. Next, the gallium oxide is one of the ultra-wide bandgap metal oxide intensively investigated in the high power and optoelectronic devices due to its unique physical and chemical properties. Despite the fact gallium oxide is not a van der Waals structure, due to the large lattice constant in a specific direction offered a way to mechanically cleave two-dimensional nanosheets similar to typical two-dimensional materials. Recently, 2D gallium oxide nanobelt exhibited a huge breakdown voltage of around 185. However, the RS memory application in the low-dimensional gallium oxide is not explored in detail. Finding new 2D material is preferred in order to expand the 2D material family. Thus, 2D beta gallium oxide gained interest in recent years and few reports are highlighted here. Besides mechanical exfoliation, hydrothermally grown gallium oxide nanosheets were investigated for the photocatalytic hydrogen evolution in 2018 and the quantum efficiency of gamma phase and beta phase were compared in detail. In 2019, a nanowire assisted uniform polygon structured beta gallium oxide nanosheets were grown and high mobility FET device was reported. Furthermore, in 2020 onwards, several DFT studies on electrical and optical characterizations of two-dimensional gallium oxide nanosheets have been reported continuously. One of such reports on the hydrofluorinated gallium oxide nanosheets provided new strategies to attain ultra-high carrier mobility in two-dimensional gallium oxide nanosheets. In terms of resistive memory application, this DFT study on the bulk gallium oxide provided deep insights on the effect of various types of oxygen vacancy in the formation of conductive filaments with respect to the lattice plane orientations. The charge density distribution analysis revealed the scope of conductive channel formation across the bulk system through oxygen vacancy sites. Alongside the PDOS visualized the contribution of atomic orbitals in the defect energy levels as well. Since 2D gallium oxide is a new candidate to RS memory, the effect of oxygen vacancy in the electrical properties and charge distribution are vital for further developments and should be realized through both experiments and theoretical manner, which has been done in my study. Let's start with the experimental study and experimental results. So first, the nanowire assisted growth of two-dimensional nanolith starts with the AU film deposition, which will act as a catalyst for the nanowire growth and then followed by a typical VLS growth process. As the target chemical vapor travels through the metal catalyst nanoparticles on the silicon substrate, the uniform nanowires are grown, and at the optimum reaction time with a unique recipe, the nanolips are formed on top of the nanowires as shown in the figures. By fine-tuning the different recipes, we have achieved to produce nanowires, nanolips, and also nano ribbons as shown in the SEM micrographs. Here are the physical and the chemical characterization results. The XRD, TEM, and the EDS mapping results provided the structural and composition information, and the bonding features are explored by the XPS analysis with the core scan spectra, which then reveal the presence of spontaneously generated oxygen vacancy along with the other species, other oxygen species in the as grown 2D gallium oxide nanolips. Earlier, our group had already published the results of single nanowire resistive memory devices. Due to the time limitation, it will be excluded in this presentation. If you are interested, please check out our publication online. The as-grown nanolips were successfully isolated and transferred onto a patterned silicon oxide substrate, and then the electrode contacts were made through FIB technique as shown in the SEA micrograph here. The typical bipolar resistive switching without a forming process was observed in the fabricated device with a low operating voltage of around plus or minus 2.5 and a very low power consumption around 100 microwatt. A consistent on and off resistance was observed during the endurance cycle test, which determines the device performance. As we already discussed, the spontaneously created oxygen vacancy is addressed through the resistive switching through SELC conduction mechanism, which actually stands for space charge limited conduction mechanism. However, much more verifications are needed. Thus, we have investigated further via DFT study. Here is the unit cell of bulk gallium oxide. The surface covalent bonds in the 100 plane or in the x direction are up to 6 electron volt stronger than the perpendicular ones, which can be broken easily by mechanical force to results in the 2D gallium oxide nanosheets. Our objective is to study the effect of oxygen vacancy in the charge distribution and the electronic band structure. So, in this study, a large 5 by 5 by 1 supercell with 250 atoms is adopted after several test runs with various configurations and size of supercell. In order to study the oxygen vacancy effect, two distinguishable oxygen atoms based on their gallium and oxygen bonding sites are removed to create oxygen vacancies. Two defect densities of 0.6 and 1.3% are used in our investigations. The Synopsys Counter-ATK atomistic simulation package was used for the DFT calculation and also to analyze the results. The linear combination of atomic orbital calculator with GGA TBE exchange correlation function was employed throughout our study. Here is the projected band structure and the projected density of states of a pristine 2D monolayer without oxygen vacancy as a reference. This is the 0.6% surface oxygen vacancy case. The projected band structure and the projected density of states visualize the position of defect energy states in the band structure. On the right hand side, the charge distribution is shown and it is found across the XY direction, XY planar direction, which is favorable for planar device structure to form a conductive channel. There is no significant change in the band gap is observed, and the positive value of the calculated defect formation energy denotes the energy is required to create such defects in the system, and in our experiment it was provided by the high temperature growth process. The band structure and the density of states for 0.6 and 1.3% defect density cases are compared here. The additional defect energy level, much deeper towards valence band minimum, is created. Valence band maximum is created at high defect density, and a significant increase in the formation energy is also observed. In both cases, the gallium 4s atomic orbital contribution is dominated in the defect energy levels. Whereas in the 0.6% interlayer oxygen vacancy cases, the P band and the P dots visualize the deep defect energy level in the band structure is just above the valence band maximum. And the charge distribution is observed across the Z direction, as we can see here, which is very favorable for the vertical device structure, which is also in contrast with our former case. Besides, the calculated defect formation energy is much lower than the former case, which is around 1.63 electron volt, which implies that interlayer oxygen vacancy is much easier to be created in the system. While comparing 0.6 and 1.3% interlayer defect density cases, in contrast to our former case, the higher defect density produced densely populated defect level in defect energy levels, and an identical increase in the formation energy is also observed. Interestingly, in the interlayer oxygen vacancy cases, the oxygen 2p atomic orbital contribution dominates in the defect energy level rather than the gallium 4s, which was dominated in our surface oxygen vacancy cases. Here is a comparison of both surface and interlayer oxygen vacancy effects in the band structure. Based on our finding, a schematic representation of electron transition between valence and connection band is drawn with observed deep defect or trap energy levels. In brief, when the system under study contains the combination of both type of oxygen vacancies, the possibility of producing conductive channel is highly favorable and will result in the resistive memory through conductive filament formation and rupture. This is my summary and conclusion. The demand for the new materials and strategies to fulfill the need of next generation technology is constantly increasing. Herein, we have explored the possibility of two-dimensional beta-gallium oxide nanoliths in the resistive memory application via both experimental and theoretical methods. The two-dimensional beta-gallium oxide nanolith device was fabricated and tested experimentally in our case. The prospects of the conductive channel formation via oxygen vacancy are investigated through first principle calculation, and the outcomes were discussed. Furthermore, higher defect density effect and the monolayer to multiple monolayer devices will be evaluated in our future studies via both experiments and simulations. Here are the references. And here I would like to show my sincere gratitude and acknowledgement to our funding agencies and my fellow lab mates and my supervisor. And thank you all for listening.